Welcome to this presentation on FastRerandomization using accelerated computing, where I'll share some insights about our latest work on scaling up experimental design for high-dimensional data. Before we begin, I'd like to talk a bit about randomized controlled trials to set the stage for what I'll talk about later on. Randomized controlled trials, also called RCTs, these are considered the gold standard for causal inference. Why is that? Well, these RCTs guarantee unbiasedness on average. If we randomize people to receive the treatment and other people to receive the control intervention, on average, the difference in outcome between that treatment group and that control group will equal the overall treatment effect of that intervention. So an example of such an intervention would be like a pharmaceutical drug, or it could be a cash transfer in the context of field experiment. However, in finite samples, simple randomization frequently produces treatment groups and control groups that have severe imbalances just by chance alone. Just by the randomization alone, the treatment group and control group in this particular study look very different. So let's take the extreme case to illustrate this. In the extreme case, where we have two units, unit 1 over here and unit 2 over here, let's say unit 1 happened to be female and unit 2 happened to be male. If we flip a coin and it so happens that unit 1 receives the treatment intervention, so let's denote that by 1, and unit 2 here receives the control intervention, let's denote that by 0 here. Now, in this small experiment, we can't distinguish whether the treatment effect is due to the treatment itself, 1 versus 0, or whether it's due to this background characteristic, gender, which just so happened to be very different by chance alone between the treatment group here and the control group over here. So this is the problem in finite samples, small experiments especially. And this problem is exacerbated when we work with modern high-dimensional pretreatment covariates. So increasingly, there's interest in using high-dimensional text embeddings or satellite image descriptors in causal inference, linking those to the experimental units and using that information to improve our understanding of the way that this intervention is working. But the higher the dimensionality of these pretreatment covariates, the higher the likelihood that just by chance alone, there will be some imbalances on some of these covariates. And this problem is even more acute when covariates are important for explaining the outcome. So if gender doesn't explain the outcome, it's not really a big deal that there's imbalance. But if gender really does explain the outcome or contributes to explaining the outcome, then the fact that there is this masking between the imbalance and the treatment effect, it leaves our conclusions less reliable than they would have been if we would have thought about how to control this imbalance. So in this context, researchers have turned to re-randomization, which is a way to address this issue. In re-randomization, we repeatedly draw candidate assignments, candidate randomizations. And what we do is we evaluate the covariate imbalance, and we only accept those that pass a stringency threshold. So let's give an example here. What we do is we generate a randomization, and then we compute the overall mean of the different covariates for the treatment group and the overall mean of all the covariates for the control group, so X of C, and we compare these. Are these two very different? Are these two very similar? And we only accept randomizations that pass a stringent threshold. So let's just formalize that a bit, and the paper goes into more details. What we do here is we shrink the expected imbalance between the treatment and the control covariates for any given dimensionality. And we can actually derive, under some simple assumptions, some theory for how this re-randomization process affects the overall mean squared error, the expected mean squared error of a particular difference in means estimate given this sort of design. So we can, in a sense, condition on our imbalance being below a particular threshold, and we can derive this formula for the average amount of mean squared error under this design, where we're only accepting those candidate assignments that have a imbalance distance that is below this threshold. So this formula contains a few pieces that I'll break down step by step. So piece number 1 is this sample size scaling factor. This sample size scaling factor states that as the sample size gets larger, as 1 over the number of treated and 1 over the number of control groups, is that as n gets bigger there, this sample size scaling term gets smaller. In other words, the bigger the sample size, the smaller the overall expected mean squared error under this design. However, there's this other term over here that's not directly affected by the sample size, but it contains these two other components. One of these components is this irreducible sampling noise, this noise that's not associated with the covariates at all. And the paper shows and discusses, building on prior theory from Morgan and Rubin, among others, that there's this other term, which is known as the prognostic variance. This is essentially the part of the covariates that affect the outcome. And as our covariates get closer and closer between the treatment and the control group, this prognostic variance shrinks under re-randomization. So we have this three-way dance between the sample size, between this irreducible noise term, and between this prognostic variance that together controls the overall degree of mean squared error. So what we get by performing re-randomization is we're able to essentially reduce this prognostic variance by making the treatment group and the control group closer to each other. And this yields these valid design-based guarantees about improved precision. So we can reduce this overall mean squared error by performing re-randomization in this sort of setting. So this is a bit of background for you about re-randomization and how it can help improve our precision for estimating these treatment effects. So let's move on to the next challenge. This is all well and good. Re-randomization helps, but as the number of covariates increases, and as the number of unit scales, the space of possible randomizations actually grows substantially. So to improve meaningful precision gains in this high-dimensional setting, we actually need to enforce increasingly stringent acceptance probabilities, holding all else equal. What this means is that if we gain additional covariates, as we move to a more high-dimensional regime, we'll need a greater and greater computation involved to get randomizations that bring the same sort of precision gains that we talked about a minute ago. So we have this compute precision frontier graph down here, where on the x-axis, we have the number of candidate draws required before we get an acceptable randomization below a given threshold. That's what we have on the x-axis. And then on the y-axis, we have the mean squared error reduction versus complete randomization, where no re-randomization was done. So this is basically the gain that we get by performing re-randomization. And when the covariate space is smaller, this gain is greater on a relative basis. So when D here equals 30, we don't need very many candidate randomizations to achieve substantial gains. However, as we move to a more high-dimensional regime where D might be 1,000, we see that we need a larger number of candidate randomizations holding all else equal in order to secure a randomization that brings an equivalent RMSE reduction compared to what we will get in these other scenarios. So what this means is that finding a good RMSE, a favorable RMSE, it gets increasingly difficult as the computation to get a single randomization grows. In other words, if I have 500 covariates, it's going to be harder and harder for me to find that one treatment assignment vector that brings about the same efficiency gains, the same precision gains as I would get from compared to the smaller sample size or the smaller covariate dimensionality setting. So this is the high dimensionality bottleneck. And to respond to that, we've worked hard to produce a solution that scales up re-randomization using hardware acceleration, using the best of accelerated computing. Experimental design requires a shift, especially for these high dimensional experiments, in how we compute, how we perform compute. These CPU-bound iterative loop type approaches are going to be too slow for our purposes here of generating a huge number of possible randomizations, and then we'll be choosing the best among those. So what we do in this work is we leverage accelerated computing, hardware acceleration, GPUs, TPUs, to evaluate balance criteria across truly a large, massive number of candidate randomizations, candidate assignment vectors in parallel. There are no other modifications to re-randomization needed here. So there is some work on sequential sampling methods for performing re-randomization more quickly. However, those sequential sampling methods usually require complex modifications to the re-randomization pipeline. Here, we require no such modifications. We use the same sort of approach that we did before, but now instead of running things on CPU, we run things on GPU where we throw these computations to the hundreds or thousands of GPU blocks across all these different blocks. These distance calculations, these assessments of how good this particular randomization is will be occurring in parallel. And these balance statistics then will be sent back to us, and we will filter them. Did this particular assignment vector satisfy our assignment criteria, or did it not satisfy that criteria? We'll be able to determine that after we perform these large scale computations all in parallel using the best of accelerated computing. And once we've done this, we'll be able to generate a pool of acceptable randomizations for, in some cases, orders of magnitude efficient from a computational perspective. So we'll be able to get the sort of gains that we needed before in those high dimensional settings. We'll be able to get those same sorts of gains that we talked about over here that we really needed a large number of candidate randomizations for. We're able to get them more efficiently using the best of accelerated computing. So that's all well and good, but there's actually another problem that we'll have to overcome. Generating and retaining millions of acceptable binary assignment vectors is going to be facing another bottleneck as our sample size gets larger and larger. If we have, let's say, 1,000 or 1,000,000 units in our experiment, every one of these candidate randomizations will be a collection of 1,000,000 numbers, and this will lead to catastrophic memory exhaustion, as we show an outline in the paper. And our solution to this is actually to separate out evaluation from retention. So instead of retaining all of the different random assignment vectors from this re-randomization protocol, instead of retaining them all, we're only going to keep the keys, the pseudo random number generation keys that were used to generate those randomizations. So for some context on that, random numbers in modern computing are generated using something called a key. So a key is going to be like a pair of numbers, or in some cases more than a pair of numbers. It could be 2 or 3 numbers, and this pair of numbers is going to basically control a random process. So once we set the key, things after that process will be deterministic. We'll be able to repeat some sort of stochastic calculation, but that stochastic calculation will occur in a deterministic way given that key. So we have this pseudo-random number generation process, which is controlled by these these keys, and these keys are what we store as we're evaluating these millions, or in some cases billions, of randomizations. And because we're saving only these keys, not these entire randomization vectors, we have considerable savings when it comes to memory. So we only save all pieces of information per randomization instead of n pieces of information per randomization. And n might get large for these large scale field experiments. This might be tens of thousands or millions, whereas L is always going to be the same. In many cases, it's just 2 integers that we'll use in these compact pseudo random number generator keys. So this is a visualization here of what will be happening. We'll be generating the keys, we'll be evaluating this batch. We'll be generating these batch re-randomization vectors. We'll be computing these balance statistics. And then after we compute these balance statistics, we'll actually discard those generated randomization vectors. Instead, we'll only keep the keys that we use to generate those randomization vectors. And given the balance statistics from this process, we'll then filter and accept randomizations. We'll store the keys of the accepted permutations, and then after that, we'll regenerate the accepted randomization vectors or re-randomization vectors on demand. And this will greatly accelerate our ability to navigate and explore extremely large dimensional randomization surfaces where the dimensionality is great and where the number of observations is great as well, reducing our memory footprint by a factor of n over L, allowing for theoretically infinite scaling as n gets large. So this is another innovation of the the software framework that we've been building up in this accelerated computing scenario. Now, what this allows us to then perform is large scale inference. So we've solved this compute bottleneck. We've solved this memory bottleneck, and now we can perform this rigorous design respecting inference conditional on acceptance. What this will allow us to do is generate a pool of accepted randomizations, and then from that we'll be able to select the randomization that we want to use in our experiment. We'll sample that uniformly. And then after we run the experiment and get results, we can perform randomization inference using that pool of acceptable randomizations that we obtained using this accelerated computing framework. And this will allow us to compute exact p-values and fiducial intervals, which will honor the theoretical foundations of experimental design while having none of the complexities of sequentially adjusted re-randomization protocols. What does this mean going forward? I think what this means is that the area of representation-rich high-dimensional experiments is really here with these innovations in accelerated computing. Now we can readily incorporate large high-dimensional covariates from deep neural networks, from visual embeddings, from satellite imagery, or from these text representations. And we won't need to, in the same way as previously, compromise on statistical rigor due to computational limits. Here, as we unify batch computation, hardware acceleration, among this sort of memory-efficient keys-only storage design, we'll be able to extend the gold standard of randomization design to the scale of modern high-dimensional data. Thank you for listening. For more information, check out the website here on the link. I'll also put it in the description for the video.